So I will talk about binary evolution in gas, and if I will have some time, I will talk about other kinds of interaction in gas, in actually protoplanetary disks. So please do ask questions if you have one. Okay, and I will start with an introduction. So as probably all of you already know, there are many gaseous media, starting with the famous AGN disks, and there are protoplanetary disks, which we all know and love. And actually, Hagai and I thought to ourselves, if we have another kind of environment in which we have a lot of gas, because it will be interesting and we can implement all the cool things from there to our new environment. And then we figured out that actually globular clusters could be such an environment. And now it's actually the time in which you should shout at me that there is no gas in globular clusters. And you will be right, because exactly. So once upon a time, not necessarily in a galaxy far, far away, we had plenty of gas. And it happened in star-forming regions, or epochs, in globular clusters. And that would be the focus of at least this part of my talk. So in case I have to convince you, dynamics in gaseous media is rich, because we have plenty of interesting of dynamical encounters and processes. For example, we have binary single interactions, we have dynamical binary formation, gas capture binaries, disk capture, binary, circumbinary disk interaction, disruption, and probably you have all the dynamical processes that you already know and love, and they are enhanced because you will have much more likelihood to have stars in this area. You will have larger densities, so it will be more likely to happen. Okay. And now we'll move to globular clusters. So for many, many years, people thought that globular clusters are very simple in the sense that they have only one population. All the stars in the globular clusters are made in the very same epoch. We have one burst of star formation. But it turns out that actually it's not the case. It turns out that we have several generations of globular clusters, and not only in such strange and peculiar clusters. It turns out that most, if not all, the globular clusters have more than one generation. So how could we actually know that? So we look at the chemical composition of objects, yes. So we have several populations, and we can distinguish between them by their chemical composition, as people saw from observations. So that's actually what led people to think about several generations of populations in globular clusters. And here you can see first generation, second generation, and extreme second generations. In some observations, there are also inferred several and further generations. And although we have the idea of several generations, we don't know where they came from. To form a lot of stars, you have to have gas to begin with, although there are several other models that suggest some other explanations for this phenomena of contaminations of stars with other chemical composition. The leading one is that we had a lot of gas that led to star formation. So we know that we have to have gas, but we don't know its source. So the source of the gas could be external to the cluster or internal. And one option for internal gas is from AGB stars. And though this plot is taken from a simulation done by Becky in 2017, and you can see that you actually, can you see that? No, you can see, okay. You can see that actually you have several generations of star formation here. So that will be the most interesting part for our thing. And the gas amount decays with time, as you might expect. And actually you have quite a few, several million years between those epochs. So we have actually a very significant epoch of gas in which we can apply all the dynamics from AGN disks, for example.
Are you going to tell us why it's episodic?
So I won't tell because I'm not sure actually. So our research focuses on an agnostic, from an agnostic point of view of the gas. We don't know where the gas came from, but we do know that we had gas in.
Yeah.
Yes.
The episodic nature of these simulations, I just wonder why it turns on and off like that.
I think that once they spill out the content of an AGB star, but afterwards another generation, yes, will be formed. I think so, yeah. Okay. And maybe another interesting feature is that the second generation of stars could be formed in disks rather than in a spherical configuration, and it will tweak a bit the velocity dispersion. Okay. Okay, and the short recap of the introduction. So we have gaseous media, and they might affect the dynamics. It could happen in AGN disks. Plenty of studies were done in each one of them. Probably I missed a ton of them, so sorry to begin with. Protoplanetary disks, and even mergers between galaxies. So practically, you can scale this very nice problem to your favorite scale, which is nice. Okay, so now the introduction is over, and it's time to introduce our main characters in this study. So practically, we have gas dynamical friction, we have free body hardening, and gravitational waves emission. So what you should keep in mind for the next minutes is that you have a binary embedded in a large area of gas, and you should ask yourself what will happen to the binary, since it's embedded in gas. So it turns out that for very large scales or separations, gas dynamical friction will dominate, and then the separation will shrink, and then free body hardening will dominate, and then the separation will shrink even further, and you will have gravitational waves emission. So practically, you can separate between each one of the processes, but we do solve the full differential equation, as I stated here, when we take into consideration all of them together. Okay, and I will talk a bit about each one of them. So for large separations, we have gas dynamical friction. So the first idea was about just dynamical friction. So you should imagine a very massive object in a sea of stars, for example. So when it travels, so actually a lot of stars accumulate behind the star, which you can imagine is a kind of friction. So this was dynamical friction, and if you replace the sea of stars with just gas, it will be gas dynamical friction, which we'll focus on. Or you can think about the duck. It will be much more nice. So actually, you should look at the wakes behind the ducks, and it will be very similar to a star traveling in the gaseous medium. But we are working on binary. It will be much harder, right? So we have a binary duck, and we will try to explain their evolution. Okay. So the equation of gas dynamical friction will be this. It scales linearly with the gas. If you have more gas, then the effect will be larger, as you might imagine. If you have more massive object, then it will also be a larger effect. And it scales with the relative velocity between you and the gas, because you should think that if you have zero velocity, it will scale differently rather than if you have a very small velocity between you and the gas. Okay. And in the intermediate separation, we have free body hardening. So you should imagine, again, our binary. And it gets kicks from a lot of stars around. So if you have, so there are hard binaries, as you probably know. There are hard binaries and wide binaries. So what defines a hard binary is your energy relative to the average velocity, mean energy in the cluster. And if you are tight binary or hard one, then your energy will be larger than the mean energy in the cluster. And if you are wide binary, it will be the other way around. So it turns out that if you are hard and you will get more and more kicks, you will become more and more hard. And if you are wide and you will get more and more kicks, you will just get wider. So hard binaries will get harder, wide binaries will get wider. That's the famous Hegel law from 1975. And actually, that will change our separation. So we want to have hard binary to begin with. Otherwise, when we will get those kicks, we will just get wider, and we want to have finally gravitational waves. Yes, Ilya?
Sorry, I didn't realize we were going to be done with the gas-dynamical friction because I had a few questions about that. So well, two quick questions, I suppose. One is, what do you assume for the ability of the gas to cool? Because your dynamical friction means you are heating up the gas, right? And if the gas, for example, if it stays the same gas and it doesn't cool, eventually the sound speed gets so large that the gas dynamical friction is no longer efficient, right? So do you assume that fresh gas comes in? Do you assume that gas is able to cool? And the second question is, what do you assume about accretion? Because in general, you have dynamical friction, and it's gas, not stars, right? Gas shocks, and gas can therefore accrete. And Bondi-Coyle tells you that actually the two are in the simple limit proportional to each other, the amount of accretion and the amount of dynamical friction. But then if you have a lot of accretion, right, that changes the properties of the binary, and can also actually, depending on the specific angular momentum, can even widen the binary rather than hardening it if you accrete gas with lots of angular momentum.
Okay, so we actually started with our analysis with a very simple prescription in which we didn't take into consideration each one of your suggestions, but then we thought actually a bit about both of them. So regarding the heating, we just did a very simple calculation of black body irradiation from the gas, etc. And it turns out that actually the gas could cool itself in a sense, but we definitely should have some more detailed analysis on that. So actually for this thing, you should think about replenished gas in a sense, because you don't carry with yourself the heat. And for the second question, so the second question was about mass accretion. So actually, we didn't look that much on this direction, but obviously a lot of interesting things might happen. So we had some simulations about mass accretion and then what will happen to them, but it's still very preliminary, but so we are not sure. But it definitely should be in a very interesting direction. I hope I answered yes. Okay. Any other questions, by the way? Okay. So we hardened the binary, and it scales with the separation, with the mass of the perturber. Of course, if you have a very massive perturber, then the effect will be larger, etc. Okay, and that's it, more or less. And finally, if everything worked well until now, we'll have gravitational waves in the Peters formula that you can't see, but you obviously know, so it doesn't matter. So we should have a very small separation, so we actually should have the gas dynamical friction and the free body hardening before that, otherwise we won't have gravitational waves. Okay, so it's time to show you some results. So you should look at this plot in the following way. So in the x-axis you have time in million years, in the y-axis you have the separation of the binary in AUs. And you can see the blue dashed line will be just the separation, the critical separation from which you will emit gravitational waves within a Hubble time. Okay, and you can see that you should first look at the, well, both of them are purple. So this purple versus this one. So at the beginning, you could see that gas dynamical friction only dominates. If you just add gravitational waves, it will do nothing practically. But then there is approximately this time scale, that if you remember, this would be the typical time scale for the gas, which we took our fiducial time scale to be 50 million years. And from this time scale, actually, we don't have too much efficient gas dynamical friction from that point. So now we should care about free body hardening. And now we should look at the second purple, and you can see that free body hardening helps a lot. But then comes the point in which actually we have domination of gravitational waves. That will be the yellow line. And all in all, we have an expected emission of gravitational waves within this time scale. So actually, we do expect gravitational waves, which is very nice.
How did you model the three-body hardening?
Okay, so practically, I'm just solving this simple differential equation in which I plugged in this formula for free body hardening.
With what is the scale is a squared?
Yes.
The interaction rate for a hard binary scales is a, and the amount of energy you remove scales is 1 over a because it's just basically equipartition. So if sorry.
Maybe I have a typo.
No,
I will check
maybe,
the units.
maybe I'm doing it wrong. Sorry, never mind.
Still, if you compare the results to actually doing it, I mean, body simulation, I'm not convinced it's the same thing.
Okay, so actually it's worthwhile checking, and maybe you are right, and it will change something. I'm not sure.
And people have done lots of these kinds of calculations.
Yes.
So you don't have to go and reinvent the wheel.
Yes, exactly. That's why I used this prescription to begin with, but maybe it might change. Yes.
Is this like an average calculation? Because you have this kind of n sigma v kind of thing, I guess. So
Yes.
I think you need to estimate it's like after many scatterings.
Well, yes, but does it actually work? Is what I'm saying. You know, how well does it work?
Well, I guess it depends on the distribution you have for the input parameters and other
Well,
things.
sure. Whether it works or not.
Actually, which parameters worries you the most?
The results depend on the parameters.
Okay.
Also for the gas, are you assuming like a constant density in these cells?
Exactly. So we have a basically decaying density with time, but we don't vary it, in distance or something, yes, yet. But we can take it into account. Yes. Okay. So it turns out that gas hardening is very efficient. So actually we bring a lot of binaries to the state of gravitational waves emission. So if we begin with a very almost the widest binary that we can, that will be the highest purple dashed line, and then we are able to merge them within a Hubble time, which is kind of great, I think. And we can merge all of them, and you can see also again the very similar scaling and shape as you did see here. We have at the beginning we have gas hardening, and then we move to free body scattering and gravitational waves by the end.
When you combine the gravitational waves and three-body scattering,
yes.
you account for the fact that three-body scattering will make the eccentricity wander, which in turn has a very significant impact on gravitational wave emission efficiency.
Okay, so in this plot we just took into account just circular orbits, but we did speak about eccentricity right here. Oh, so sorry. Actually it's a perfect question. Thank you, Ilya. So what happens in eccentric evolution? So I think the most interesting thing about gas-dynamical friction is that actually the most important point in your orbit is actually the point in which you have the small relative velocity, because then you will have stronger drag. So actually it's not the pericenter, but the apocenter. So actually what happens with eccentric orbits is the following. So we actually went back to our equations and we plugged in an eccentric orbit rather than the circular one. And we had those disgusting equations, which I will scroll over very fast so you won't kill me. And we had some merger timescales which would be much shorter actually, because you should think that what happens is that you should have very small pericenter in which you will be able to emit gravitational waves, and it happens in a shorter time scale. So that's what happens here. And actually you have eccentricity excitation, which might be counterintuitive if you think about it for a minute, because usually you think about, I don't know, for AGN disks, etc., you should think about gas-dynamical friction as something that circularizes your orbit. But it's not the case here, and it scales actually with the density profile of the disk or globular clusters or whatever, and it turns out that you have a critical power law from which you will have a circularization, and another one that from which you will have eccentricity excitation. So in this case, you actually get more and more eccentric. That's for flat density distribution. And what happens is that as you get more and more eccentric, your pericenter is smaller, and then you emit gravitational waves in a shorter time scale. So the dashed line will be the pericenter, and the solid line will be just the same major axis, as you can see here. And those are just the orbit average calculations. Other interesting things might happen in the non-averaged calculation. So we actually worked on the n-body simulation for the gas just to compare between them, but that actually belongs to another project that I will discuss in a minute. So to sum up this part, so what is the difference between eccentric and non-eccentric binaries? So I just took, for example, the mean eccentricity if you think about a thermal distribution, so it will be something like 0.66. So it turns out that the timescales are much shorter in the eccentric orbit, as I told you earlier. In the circular orbit, you will have something with larger timescales. The regimes of dominance, you just move from gas-dynamical friction to gravitational waves. You don't need, in a sense, the free body hardening to have gravitational waves. But in the circular case, you do need. And in the in terms of observed eccentricity, as you can see here, you might have some remaining eccentricity even in LISA measurements, which might be very interesting, I think. Okay.
Can I ask you start with 1 AU separation, I think.
Not in all of them.
And you want, purple one, right? And you want this all to happen while the gas is still around, but presumably it's not there for very long.
So I don't care about the gas for a very long time scale. Then I just want the binary to approach the critical separation from which free body can take
But
it.
you just said that you could even skip the three-body scattering.
So it depends, because if you are very eccentric, you see that the time scale are very short. And then you could just allow yourself to skip all of them.
Yeah. If.
Yes.
So you've got to start with a whole lot of super eccentric binaries to do that.
So actually, as I showed, gas-dynamical friction might excite, yes. The electricity depends on and then it might happen. Or if by chance you start with very eccentric binary. Okay, so until now I talked just about some individual cases, but it's time to estimate the number of mergers from this channel. So you have the famous formula if you want. So you think what will the fraction of stars in the disk of second generation, what will the survival fraction of binaries from stellar evolution, what will the fraction of stars with masses larger than 20 solar masses that will be our progenitors, what will be the retention fraction, because some of them will be retained from the cluster. We don't want that the other way around, but fine. And what will be the merger fraction that will be derived from our model, as I showed you earlier. So as we calculate all of them, it turns out that we can be in the measured rates. So it really depends because we want to have gas in our cluster. So it could happen if the cluster, in the very initial stages of the cluster. So it could happen if close enough, if the cluster is very young, that will be young massive clusters, or in old globular clusters, and then we will have a delay time. Okay, so this will be future implications for this part. So what? Yes.
Wait, how massive are your young massive clusters?
Something like 10 to the 5.
Okay,
Yes.
So, okay, quite massive. Okay.
Yes.
And the velocity, the escape velocity is something like 10 kilometers per second?
It should be something like that, yes. Maybe a bit larger.
I was just wondering, so I think there the issue is that three-body interactions can actually hurt you because they eject the entire binary from the cluster with a high probability. Once the binary is hard enough, a
Yes.
single interaction it'll harden the binary, but it'll eject it, and then unless it's hard enough, it's now sort of stuck because there's no more interactions, no more gas, just sitting out there floating around.
Okay, so actually that's a nice direction. Okay, yes.
So have you included the ejection probability for the binary?
So not for that. We just took the retention fraction. That's it. So maybe it could be encapsulated in some magical way, but we did it directly. So future prospect and implication for this part. So we are setting initial conditions for other gravitational waves channel because it happens very early in the cluster evolution. So we could modify the separation distribution. For example, we could have a pulsar retention fraction that will change because we could accrete gas from second generation stars, etc., and then they won't be able to be ejected out of the cluster. We could modify the spin distribution either by accretion or by merge them. We could have, I didn't mention it, but we could have hierarchical mergers in gas in which we'll have more and more massive objects due to those mergers. And we could set constraints on the gas amounts in global clusters. You can reverse the whole model on the other direction and think about what we could say about the amount of gas in the clusters from the observed data that we have already. And we can also form short-lived binaries, and that's what I will talk about now. So gas can actually assist in binary formation. So you should imagine a Hill sphere. So it actually it is termed as the L2 mechanism for planetary formation of binaries in the Kuiper belt. So you should think about a very large Hill sphere filled with gas, and then you have around the black hole, and then another black hole penetrates the Hill sphere. And if it dissipates enough energy within the Cosine timescale, then you will form a binary. So that's what's happened here. And we thought to ourselves, maybe we could have something like that in our globular clusters. So Tagawa mentioned it for AGN disks, and we had it for Kuiper belt objects, and then we thought what will happen in our case. And we have a very nice simulation done by Alexei Generozov. Okay, so I will show it twice because probably didn't have enough time. Okay. So that's a way practically to form binaries. And what Alexei did, he ran several n-body simulations of 2 bodies plus gas to try and understand what will happen in captures in globular clusters, for example. And I did the calculation I will show you in a minute. So now you should ask yourself, what will be the conditions for gas-assisted binary formation? So first, you have to have a dense enough region in terms of stars and gas, because if you don't have one of them, you can't form a binary. Yes.
I know I'm sharing, but I mean, maybe a bit about the Hilo radius, because I think at least in the AGN disks, the reason you have a Hilo radius is because you have a very supermassive black hole, so you can have the style separation. So what's your Hilo radius in the cluster case? Do you have like you assume some massive INBH in the cluster or something like that?
So you have cluster potential to begin with, so it will be the masses over the 2 stars or black holes to the third times the radius of the cluster to begin with.
This is like the Tyler radius.
In a sense, yes.
To the cluster.
In a sense. Actually, I will show you that the Hill radius is not definitely the smallest radius that you can think about, but it gives you a cutoff. Because the stars should be, to begin with, they should be close enough that they will feel just each other and not the whole potential or other stars or whatever. Because if they are too far, then you won't be able to capture a binary because they don't know about each other. That's more or less it. Okay. Okay, so you should have close enough separation that relates to that, and you should have a slow enough velocity, otherwise they will just fly by each other. And now we could calculate the rate using all the ingredients I told you earlier. So we have the density, that will be n, the Hill radius, z will be the minimum between those two. In the unfocused case, it will be just the Hill radius squared. And we have the relative velocity between them and the distribution of relative velocities, which we assume to be Maxwellian. And there is a critical velocity which we calculate, I won't show you here, which is calculated by equating between the energy dissipated by the gas and the energy of the binary. And by that, we actually derive critical velocity for different occasions. For example, in the supersonic case, in the subsonic case, or if you have one in the subsonic regime and one in the supersonic regime. And actually, there is a gentle point here, because if you want to capture, you want to move between your highest point of velocity, so your initial velocity, to the final capture velocity. So actually, you should take, in a sense, the minimum of the critical capture velocity. And unfortunately, it turns out that the process is not always efficient. So, for example, you should think about those 3 examples. So it turns out that for our fiducial model for globular clusters, captures won't be that promising. But for AGN disks, for example, we might have a lot of captures. And so does for Kuiper belts. And actually, once we have more than one capture within the timescale of the gas, then we could have a lot of interesting dynamics. For example, super scattering, in which you have a binary, and actually it got closer and closer, but then another one will come because it also scattered to the Hill radius, etc. Or enhanced feeding, if you have a black hole and then you scatter another one, and the black hole will be just fed by external objects. And takeaways from this part, globular clusters tend to host multiple generations, and star-forming environments are gas-rich. Gas dissipations assists in hardening, and it also affects indirectly on other gravitational-wave channels. And by that, actually, I will ask if you have questions. Otherwise, I will move to completely another topic. So, do you have questions?
Sorry, I think I'm still not quite sure I understand what is the Hill radius that's relevant here. So can you explain? Actually, can you tell us what exactly is the Hill radius of your ball of gas?
Okay. So what I did, I just took the mass of the binary, let's say, over the mass of the whole clusters, then the power of third, then times.
Pores, really?
Yes, actually, yes. So actually, in a sense, it is the Hill radius versus the potential of the cluster or the core, if you want to think about that.
These Kuiper belt objects have the advantage of being more or less in a disk. That helps. I have wondered whether it might happen in these AGN disks, but for a spherical distribution.
So for second generation, you might have a disk of second generation formation. So it might be actually very similar to AGN disks in that sense. Again, I think this Hill radius just gives you an upper limit rather than an actual radius from which you'll have an interaction. Because you could, yes.
Sorry, I think we interrupted you before you actually finished saying what the Hill radius was. Okay, so it's the ratio of the mass of the binary to the mass of the core of the cluster to the 1/3 power.
Yes.
Right? Times
The distance to the center.
Yes.
the distance of the binary to the cluster.
Well,
And-
you've got single stars and they capture each other, right? So it's, yeah. Well, so, yeah. So it's really, it's the Hill radius of a star, given that it's orbiting the center of the cluster or the massive object or whatever. And you need the second star to come within that Hill radius to be overcome by its gravitational potential of the star. So the mass interior to that star, I mean, you have to give us a feel for the distances from the centre of the cluster. I mean, usually we talk in units of core radius and so on. So where is this mechanism efficient? How far from the core, from the centre?
So definitely it will be more and more efficient as you are closer to the core and actually focused inside.
Yeah, but the reason Kuiper belt objects are binaries happily formed is because they're far from the sun.
Yes.
So you can't, it's very hard to make them, if you like, in the asteroid belt, for example. So you need to be far, not close.
Okay, so if you are closer, you will have larger density, I guess, but you will lose some other parameters. So actually, yes. I think you're right.
Yeah, okay, the cross section, yeah, okay. So there must be a sweet spot.
Yes, exactly.
Right, yeah. Wonder what that is.
Okay.
Any questions on that? Can you maybe comment?
Sorry.
Yeah.
Just wondering if you had any sense of like what fraction of the current population of gravitational waves might come from this channel.
So it really depends on the amount of gas that you had. So we might actually reproduce everything or comparable to the current observable rate, but it could be much smaller. It depends how much gas you had and in which epoch and on which redshift, because it should be the formation of gravitational waves from this channel should be very close to the gaseous epoch, which should be in very early stages of the gas formation, on the cluster formation actually.
Yeah, I was about to ask, like, in a similar direction, like, regarding the gas budget. I think you motivated initially that you have this exotic star bursts, and I think they kind of live like a few mega years. So, and yeah, I'm just wondering, I mean, what's your gas lifetime, and have you tried probing different gas lifetimes and see the effect of these results?
Yes. Okay. So, from this simulation, for example, you have quite a few tens of million years. But we actually tried several time scales. I think I don't have it in this presentation, but definitely in our paper. So obviously, when you have shorter lifetime of the gas, then everything is less efficient, and the other way around.
So they don't know how long such gas stays around, if they don't know.
But maybe it would be nice, you know, let's say you have a critical lifetime for which 10 AU binaries could migrate.
Yes, definitely there is one, and it would be very easy
like
to.
critical threshold.
Yes.
Field. So that would be nice.
Yes, as I told earlier.
Comparable to, you know, AGB wind load mass loss timescale, for example. That would be
By chance, yes. So you could actually reverse the whole model and ask yourself what will be the assumptions that you should apply on the globular clusters if you have such and such mergers. So that's actually another point of view.
Right, so I think presumably in globular clusters the problem is, or in star clusters in general, that at some point the gas is evacuated by supernova.
Yes.
So you have only a few tens of millions of years, actually less in some cases, depending on when you think the first supernovas are happening. Really probably within 10 million years you start having supernova explosions. But in an AGN disk, I guess it's just a lifetime of the disk, which is order of 100 million years.
Yes. Okay.
Can I ask you one question, I promise, on the rates?
No. Yeah, of course you can, yes.
Can you just go to this trick equation on the rates that
Yes.
Yeah. So I think, obviously it depends on the number of the stars and other things, and also on the survival binary fraction, but have you tried actually changing like the fraction of primordial binaries actually formed during this?
So I don't remember if we did that. We definitely have a table of tweaking a lot of parameters, but I don't remember which we tried. So I will send you in politely to our paper. Okay. Any other questions?
Well, if you had, what about having an intermediate mass black hole at the centre and with its own personal disk, you know, that might help with these things. No, we don't know if they exist.
Yes, okay. So to begin with, I think there are plenty of uncertainties in all those second generation formation, etc. But something, you should have gas at some point. So that was our...
Well, as you say, these second generation and third whatever, they're there looking at it.
Yes.
So, you know, somehow.
Yes,
they got
somehow we had gas. We just don't know how.
Yeah.
Yes. Okay. So if there are no more questions, I will just move to complete another topic. Okay, so complete another topic. I will destroy planets. It will happen in a minute.
15 minutes, including questions.
Okay, I can destroy planets very quick. Okay, so I will talk about the Oil and Erosion. So actually, the only link between the different topic would be just gas. I thought you would be interested also to hear about planetesimals, etc. So actually, it turns out that planet formation is a very challenging process because you should move from various different timescales, and you should build your planets from a very, very small dust objects. So you actually begin with 10 to the minus 4 centimeter objects, and you should have a planet by the end. So it's very, very challenging. So we know how to explain planet formation in the very early stages. So we have just sticking, for example. You should think about, I don't know, dust in your vacuum cleaner, for example. So it's the very same process. But when you arrive around meter-sized objects, then you have plenty of barriers. So you have fragmentation, for example. Two large objects collide each other, and then they break each other. That will be fragmentation. And you have radial drift due to the pressure. Actually, pebbles are going into the star rather than just going, and many others. And once you actually pass this barrier, then you know how to explain the growth of very large objects. For example, by pebble accretion, in which you have a very large objects that accrete small pebbles into it, or core accretion. Okay, so what I will suggest here is that the process of planet formation is not hard enough, so we should suggest another barrier, which we will term as the Oil and Erosion. Okay. Okay. So I will begin with convincing you that you actually know what erosion is. So you should think about a pile of sand, and then the wind comes and blows and takes the upper layer of the dust of the sand. And actually, this will be wind erosion, and we have a very similar process in protoplanetary disk. And you could also think about water erosion, in which you have pebbles, real pebbles, not the ones from planet formation, inside the river, and they are shaping according to the water, actually. So there are three types of oil and erosion. So if you have a very, very heavy rock, it would be just creep, because the wind is not strong enough. The rock will just roll over the place, and we won't have erosion in a sense at all. If you have a slightly less heavy rock, you will have saltation. So the wind takes the rock and then smashes it into the ground, and you have a lot of small particles from the rock. And if you have very small particles, then you have suspension. So the wind blows and takes the very small particles, and they never come back, at least in this length scale. So I will try to convince you that suspension actually takes place in protoplanetary disks. And it's purely mechanical process. There is nothing with high temperatures. It's not thermal ablation. And gas drag is basically the wind. You should think about the car and you, I don't know, with a hand outside your car, so you will feel the wind. It will be the very same process in a sense. And the lifted particles are very small. It fits to suspension rather than any other process. And self-gravity is basically negligible below 1 kilometer. So practically we have just the cohesion of the particles, van der Waals processes, for example, versus the suspension, and that's it. And of course, that suspension requires a threshold velocity, because if the wind is too weak, then you won't have any kind of erosion. So the wind should take over the cohesion, and actually that allows you to derive the threshold velocity from which you have erosion. And that will be this velocity. It scales with the size of the particles inside the large objects. That will be d, the density of the gas, and some constants. I will move forward. And above this threshold, the erosion is actually very efficient. And you can derive it analytically. It scales with the relative velocity between you and the gas, the cohesion between the particles inside the pebble, the radius of the pebble, etc. So that would be it. Okay. And I will show you some results. So it turns out that ion erosion is very efficient. Timescales are very small. Usually in astronomy, we don't speak about just such small timescales. And we actually could grind down particles from the size of meter size or a bit larger to actually centimeter size, which is actually very nice, I think. And the oil and erosion gets stronger as we get closer, because then you'll have more and more gas and more headwind. So you should think about the distance between you and the star, and as you get closer to the star, you'll have smaller final sizes. And I will finish by that, I think. So oil and erosion actually enriches also the abundance of small objects in the disk, because we have abundance, now we have abundance of a lot of small objects. So once you can form a core or something, then your pebble accretion or core accretion will be way much more efficient, because you will have a lot of small particles that could be accreted on the object. So by that, I think I will close. Thank you.
Okay, thanks, Mor. Any questions on any of the? Go ahead.
So the erosion story, I wanted to understand a little bit better. So the gas density here is much smaller than the pebble density, right? So why, even if the gas velocity is high, why wouldn't it just sort of make its way around the pebble, right? I mean, if I, look, if you, if I come over to Guinea and go, poo, right? His nose is not going to fall off, even if I blow the air pretty hard, because the density of the air, if I put him in front of a fan, right, it's not going to make parts of him fly off.
So it depends on several parameters. It depends on the velocity of the wind, the velocity of Yevgeny, and actually the chemical composition of both of them. Because if you will blow a very dusty wind on Yevgeny, then some of it might stick. Depends on the velocity. If you will be very supersonic, then nothing will happen and it will just go through it. Yes, so I think it depends on.
If I'm actually supersonic, right, can't I actually form some kind of a bow shock, and maybe that protects Yevgeny, because now, I don't,
Exactly.
the wind doesn't hit Yevgeny, it hits the shock that's sitting in front of him.
So if
Yevgeny is very scared. Right, so.
If it's supersonic, I think you're right, and nothing will happen. So actually, there is a velocity in which interesting things will happen. Yes, if you're very slow, also nothing will happen, right? So.
Any more questions without violence, please? Yes, Rio.
Well, just to follow up, so in that case, would the pebbles even form in the first place? Like, if the erosion's that, if your erosion is 10 to the minus 9 megayears, which is like a day or less.
So actually, I started with a distribution of objects to begin with. I didn't ask myself where did they came from. As I told you, in this project, we just tried to ruin plant formation, not to help them. So we succeeded in our own way. Yes. Any other questions? Yes, please.
Just want to check I understand. So are you saying that this explains like why all the pebbles on the beach are the same size?
So actually, it might be the case. Actually, we discussed a bit pebble accretion and the final size, etc., and how it actually will help also streaming instability. But we didn't check it, I think, versus observables yet, if that's the question.
So what determines this final size? What does it depend on?
So for example, as you can see from this plot, one parameter is the distance between you and the star. As closer you are to the star, then erosion will be much more important. That's one parameter. Also, the cohesion forces inside the planet, the size distribution inside the pebble, a lot of parameters basically. But for each set of parameters, you have one final size, in a sense.
I think as the size of the pebble goes down, your relative velocity becomes lower and lower until it's actually below the threshold for this thing to operate.
Actually, it relates a bit to Ilya's question, I think, also.
Is there a formula for the final size?
Yes, but I think we don't have it here. Yes, so there is. I think there is, yes.
There is, yeah. Could you go maybe to the relative velocity threshold?
You mean this one?
Whenever you have the relative velocity smaller than this thing, you will have the final size, and that depends on the Stokes number you have. I have to follow up paper, but that's the point.
You should check for Grishin et al. 2021, yes. 20.
Yeah, but generally I think each location in the disk will have a different critical Stokes number for this to stop at.
So the different beaches have different pebble sizes? If I go to the beach with a more wind, are the pebbles like smaller than the beaches with no wind?
Could be, yeah. It also depends how dense the air is. So maybe a beach on the Everest is going to be different from a beach in Melbourne, probably.
But I think we finally found our referee. So 2 years ago, someone asked us about sands in the beach, but we didn't know who was it, yes. We will talk a bit later.
Okay, so if there's not many burning issues, let's think more again.